In this video, we're going to talk about Poisson probability distribution. So Poisson probability distribution is a probability distribution used to count the number of occurrences of a particular event within a specified interval. So let's take a look at an example. The number of phone calls to IT is 5 per minute from 12 p.m. to 1 p.m. Let X be the number of calls received from 12:10 to 12:20. Well, a couple of things here. This would be your average, which is one thing you'll want to look for. And here is a particular interval. In this case, it's a time interval, but it doesn't always have to be time. Okay, I've listed out the conditions that are needed in order to have a Poisson process. Now, Poisson probabilities are used to determine the probability of the number of successes in a fixed interval of time or space. So the Poisson probability distribution function. If X is the number of successes in an interval of a fixed length t, then the probability of obtaining X successes in the interval is given by this formula, where lambda represents the average number of occurrences of the event in some interval. So again, we won't be using the particular formula. I will show you how to put this into the graphing calculator. Okay, let's take a look at an example. So a McDonald's manager knows that the cars arrive at the drive-thru at the average rate of 3 cars per minute between 5 and 6 p.m. Determine the following probabilities. Now, similar to binomial, you got to put it in one of two ways. Either x is equal to little x, which is the PDF, or x is less than or equal to x. That's going to be the CDF, and I'll put probabilities. Now, for the PDF, it'll be Poisson PDF, and it's lambda times t, comma, x. For the CDF, it'll be Poisson CDF, and it's lambda times t, comma, x. Okay, so now let's take a look at these. So exactly 7 cars arrived between 5 and 5:05 p.m. Because it's exact, I know this is going to be the Poisson PDF. Well, lambda, it talks about 3 cars per minute, so lambda will be 3. Here, the time is going to be 5, and the x value that I care about is 7. So it's Poisson PDF, lambda times 3, lambda times t, that's 3 times 5, that's 15, comma 7. Now, let me show you how to put this into the calculator now. Okay, so how do we put this in? Hit second and then vars, and now we're going to look for Poisson PDF, which is going to be letter D. Well, again, the mean, this is going to be where the lambda times t is going to be. So in this case, that's 15. Hit enter. And the x value is 7. Hit enter. Highlight paste. Hit enter. Hit enter again. And rounding to 4 decimal places, that's going to be 0.0104. So let's write that on the paper now. Okay, so we've written that out. So now I'm going to write out what the interpretation would be in the context of this problem now. So on about 1 out of 100 days, there will be exactly 7 cars that arrive at the McDonald's drive-thru from 5 p.m. to 5:05 p.m. Okay, let's take a look at the next example. So more than 4 cars. So that's the probability of x is greater than 4. Which again, we need to rewrite because it's not x is less than or equal to. So we'll write out its complement, 1 minus the probability x is less than or equal to 4. So again, lambda is 3. In this case, again, t is equal to 5. And the x in this case is going to be 4 because it's less than or equal to. Okay, so how do we put this in the calculator? 1 minus Poisson CDF, lambda times t, that's 15, comma x, which is 4. So let's put this into the calculator now. Okay, so first off, 1 minus, and then hit second, vars. This time we're going to do Poisson CDF, which is letter E. So again, remember the mean is lambda times t, so that's 15, hit enter, and 4, hit enter, hit enter, and to 4 decimal places, that's 0.9991. So let's put that on the paper now. So here it's 0.9991. Okay, let's take a look at the next example. So the probability that at most 5 cars arrive between 5 and 5:02 p.m. So that is the probability of x is less than or equal to 5, which is good news. We can put that in immediately. Lambda's 3. T in this case, that's 2. And x is going to be 5. So that's going to be Poisson CDF, lambda times t, that's 3 times 2 is 6, comma x, which is 5. So let's put this into the calculator now. Okay, so hit second vars, and we're looking for Poisson CDF again, which is letter E. Okay, so lambda times t here, that's 6, hit enter. Then x is now 5, hit enter. Highlight, paste, hit enter again. And rounding it to 4 decimal places, that's 0.4457. So let's put this on the paper now. So there's our answer for this problem here. Okay, let's take a look at the next example. So the Food and Drug Administration sets a food effect action level for various foreign substances that end up in the food we eat and liquids we drink. For example, the FDAL level for insect filth in chocolate is 0.6 insect fragments per 1 gram. Suppose that a chocolate bar has 0.6 insect fragments per gram. Compute the probability that the number of insect fragments in a 10-gram sample of chocolate is the following. So, first of all, being able to identify that is what your average is going to be. So lambda is going to be 0.6. The sample, or the interval at this case, is going to be 10 for these problems. Okay, so let's take a look. So exactly 3. So here, that's the probability of x is equal to 3. So this will be a Poisson PDF. So lambda is 0.6, t is 10, x is 3. So lambda times t, that's 0.6 times 10, that's 6, comma 3. Putting that into the calculator, we get this. So now I'm going to write out the interpretation in the context of this problem. So about 9 out of 110 grams of chocolate will have exactly 3 insect fragments. Okay, let's take a look at the next example. So here we want it to be fewer than 3. Well, that's the probability is x is less than 3. The problem is that's not x is less than or equal to something. So here we'll write it as x is less than or equal to 2. So again, lambda 0.6, t is going to be 10, and in this case, the x is going to be 2. So now this is going to be a Poisson CDF. Lambda times t, that's 6. That's 0.6 times 10, comma x, which is 2. Putting that into the calculator, we get this. Okay, let's take a look at part C. So at least 1, that's the probability of x is greater than 1. Well, that is exactly the same thing. Using its complement is 1 minus the probability is x is less than 1, which is exactly the same as 1 minus the probability that x is less than or equal to 0, or I can write it as 1 minus the probability of x is equal to 0, which is what I'll use here. Okay, so lambda, 0.6, t is 10, and in this case, x is 0, so it's 1 minus Poisson PDF. Lambda times t is still 6, comma x, which is 0. Put this in, and we get 0.9975. Okay, last thing I want to talk about is the mean and the standard deviation of the Poisson random variable. Those formulas are given here. So we can always rewrite the formula instead of lambda t, just call it the mean for that. All right, so let's take a look at a quick example. In Kingville, the number of potholes on a major street is a rate of 3 per mile. Let x represent the number of potholes in a 4-mile stretch. So for part A, I want to be able to calculate the mean. Well, the mean is just going to be lambda times t. Well, the rate is 3. We're dealing with a 4-mile stretch, so it should be 12 potholes. The standard deviation for us is just going to be the square root of lambda times t. Well, we know that's the square root of 12 thanks to part A. And rounding to 1 decimal place, that's going to be 3 5/10.